Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hi everyone, today we have with us Otto Mustonen, who is a postdoctoral research associate at the University of Sheffield in the United Kingdom. Hi Otto, wonderful to have you on Real Scientist Nano. How are you?
I'm doing great. Thank you very much for having me. It's great to be here.
Great. Let's start with your scientific journey so far. So how did you end up at Sheffield doing a postdoc? Tell us about your scientific journey.
Well, I was a little bit of a lonely kid when growing up, and I had this idea of like, wouldn't it be great to be a lorry driver? Like that's a job where you don't have to interact with other people too much.
Right.
And then it all went wrong. I did not become a lorry driver. I don't even have a driver's license. But I did end up doing something else. I ended up doing science. And science, despite the stereotype, is still not something you just do by yourself. Science is something you do in teams.
Right.
So when I was a kid, slightly after this lorry driver career plan, where I grew up in Finland. I'm from Finland, near the capital, Helsinki. And there was this science center or museum, if you will, and they were, of course, doing lots of outreach. That's what the whole thing was about. Mm-hmm. And I always enjoyed visiting there. And my mom, she signed me up on these short courses in the summer because she wanted to, have some time of her own.
Makes sense, yes.
And we used to do all these cool things on these courses. Like we would do things like classical, kids science experiments, like, the elephant toothpaste, always fun. We used to do bottle rockets with water and dry ice. Mm-hmm. Lots of fun, that sort of things. So like looking back, I think that was probably like that outreach was probably had a lot to do with me eventually ending up doing science. So to me, like looking back, it's like, well, outreach actually is really important. Mm-hmm. Mm-hmm. When I was finishing high school, I was really interested in chemistry and physics and math. And I had to decide like, okay, what do I want to study at university? Should I go for physics or should I go for chemistry? Uh-huh. And I ended up going with chemistry.
Right.
I like doing experiments.
Okay.
And but then a couple of years into my undergrad, I learned about solid state chemistry, and I learned that you don't have to choose between chemistry and physics. You can just do both.
Absolutely, why not?
Because in the solid state, they're just kind of the same thing.
Absolutely, yes.
So I became interested in solid state chemistry, and then I was very lucky. I got a summer internship at a research group at my university, and that was actually paid, so that was nice.
That's good, yeah.
And that's when I kind of fell in love with research. I was lucky enough to have a very good PhD student who was close to finishing her PhD. And she was an excellent mentor to me, and I was like, wow, I want to be like her. I want to be like know everything and like do all these cool experiments and that sort of thing. So I think other than the outreach, I feel like mentorship is really important and having role models.
Absolutely. Yeah, that makes sense. Yeah, absolutely. That's really interesting. Yeah, please go ahead. Sorry.
No, that's all right. So then I ended up doing my master's and then PhD at this group. I So when I was working with this PhD student, we were doing magnetism, and then in my master's, I was doing batteries. I actually worked for a battery company for a while.
Okay.
And I had to make this choice of like, should I get a normal job, go into the industry, or should I stay in the research? And I decided, okay, I want to do what I think is fun, and that's research.
That makes
sense. That's what I'm doing. And then I ultimately ended up going back from batteries back to magnetism and these quantum materials type of things, because that was the most interesting thing to me. So there are people who have like more noble motivations, like I want to do science because I want to help people. Like I feel like my research area is super important. And sadly, I'm not one of those people. I just do things because they're cool. And like somebody even pays me to do this stuff. Isn't that crazy?
Yeah, that is true. I mean, it all comes down to that, right? Are you having fun with whatever you're doing? That's how I go about it. Am I having fun with what I'm doing? If yes, then yes, that's what I want to do. That's how I make my decisions mostly as well. So I completely relate to what you're saying. Absolutely.
Yeah. So I did all my degrees, including PhD in Finland, and then my friend found this job advert that was like, well, that would fit me, and yeah, that's how I ended up in Sheffield.
Okay, that's quite a journey from wanting to be a lorry driver to being a scientist now, a postdoc in Sheffield. That's quite a journey you've had. So your current research, you did speak a little bit about it in the short podcast, but if we were to go a bit more in detail or zoom out a bit, so where does your current research fit in this big picture of materials or nanoscience?
That's an excellent question. So my kind of the broader research area is quantum materials. So materials where all these weird quantum effects actually results in something, in some new properties or some new types of states. So of course all materials, quantum mechanics affects all materials. But this is kind of a subset of materials where the quantum effects are especially strong. And really, I think this is an area that is at the intersection of solid state chemistry, condensed matter physics, and materials science. So there's really, in terms of like what I do myself, I do a lot of experiments at these large facilities, and many of them are experiments that are mostly done by physicists.
Okay.
So some of the experimental techniques I use could certainly be classified as physics, but then ultimately I'm a materials chemist. So what I do, my job, the way I see it, is my job is to make new materials.
Right.
So I'll use some cool techniques to characterize them, but at the end of the day, I need to make new materials. If I'm not making new materials, then I'm not doing my job.
True. Okay, so you're making new materials with some fancy equipment and fancy techniques and fancy labs and expensive experiments. Is that correct?
That's mostly correct. So sometimes a lot of the materials that I use, like the materials that I make, I'm not using fancy pants techniques to make them.
Okay.
But I'm using fancy pants techniques to study them at very low temperatures.
Okay.
So a lot of materials, they're not nanomaterials, they're just normal ceramics. So I just mix them up and I heat them up, and then I bake a nice material cake, and then
And then you use the fancy techniques. You're like, okay, what property do you have? How do you behave if I go down with the temperature? How do the electrons move around and stuff like that? That's what you do, right?
That's what I do. Yeah.
Okay. That sounds cool. I think I understand this a bit more now. That makes complete sense. So it does sound to me, you did already mention that you're mixing up materials, making some nice cakes. So it sounds like you have done a lot of interesting experiments or have been involved in a lot of interesting research projects. And I know this question is tough because if anyone were to ask this question to me, I would also not be able to pick one. But if you have to pick one experiment or research project that you're most proud of, or the most quirky or fun one, could you pick one and explain it to us in simple words in the section we call In Other Words?
I'll try again with the simple words. I'm not sure how that will go.
Let's see.
But I'll give it my best, and we'll see how far that goes.
Absolutely.
So one of the main areas that I'm looking at in terms of quantum materials are these materials known as quantum spin liquids. Mm-hmm. So I explained some of this in the short podcast. Mm-hmm. So these are materials where you have spins or these tiny magnetic moments, and then how they are arranged with each other, or what is the lattice, then affects a lot of like what the properties are. So a lot of people are looking at things where you arrange your tiny magnets or magnetic cations, often, for example, copper ions. You can arrange them in triangles so that you have a lot of triangles.
Right.
Or you can arrange them as honeycombs, or you can arrange them as this fun Japanese basket weaving technique. So there's a lattice called kagome, which really comes from basket weaving. But I mean, I wish probably doing the basket weaving would be at least as cool as doing this research.
We are good with simple words. Yeah, I think I'm with you so far. Go on.
And one of the way you can arrange these cations is squares. And one of the reasons why squares, and certainly squares of copper ions, is important is because this is how superconductivity works in the so-called cuprate superconductors. So this was a really big deal in the 80s. So they gave the Nobel Prize for this like the year after they found these.
Okay.
So these were superconductors that have a superconducting transition temperature that was larger, much larger than was thought possible from theory.
Right.
And in these materials, they are layered materials, and the superconductivity actually happens in this square layer of copper ions.
Right. Okay.
And back when this was, the new cool, really cool thing, I still think this stuff is so cool. But that's me. There's not that much research funding in it anymore. A physics Nobel laureate called Philip Anderson, he made some predictions that in this square arrangement of these coppers, instead of superconductivity, you could also have a quantum spin liquid. So you could have a state where the spins, or these tiny magnets on these coppers, would behave in a liquid-like manner, even at absolute zero, where there is no thermal energy. So they shouldn't be moving. The spins shouldn't be moving at all. Mm-hmm. But because they are quantum mechanical things, it's in some cases it's possible. Mm-hmm. Now the thing is, nobody found a material that would do this for a very long time. Right. So there are quantum spin liquids where you have different arrangements. There are quantum spin liquids, especially with the triangles and the Japanese basket weaving. Mm-hmm. Lots of quantum spin liquids in those, but nobody found a quantum spin liquid on the square, even though there are dozens, maybe hundreds of theoretical predictions of what would happen.
Right.
And I was the first. So, well, not me, our group was the first group to make a candidate material for the square type of quantum spin liquid. After, it was predicted 30 years earlier, and we made the material that maybe works, maybe doesn't, but it's certainly the first candidate. And that was sort of fun because I had this research idea, and it was really simple. Mm-hmm. The idea was that, well, we have a square compound which mm-hmm. has a certain type of interactions, and then we can change one atom, and we have the same square, but different types of interactions. And if we look at the theory, somewhere between these two should be a quantum spin liquid. And my idea was just, okay, let's mix these materials and see what happens in the middle.
And it worked.
And it worked.
That is so cool. That is, wow. Do you remember the feeling when you first realized that, oh shit, this actually work? Do you remember that moment?
Yeah, oh, absolutely. So that was certainly one of my favorite. So my favorite part of the job is going to do these cool experiments. Mm-hmm. And that's really like you're condensing like months or even a year of work into just a couple of days. So it's like you get to travel somewhere, you get to do a cool, expensive experiment, and ultimately you find out in a day or two. You find out, did it work? Did it not work? And that's the coolest part. So we were pulling like really long days in Switzerland at this neutron and muon facility there called the Paul Scherrer Institute. Uh-huh. And we cooled down our sample and it was like, oh, it worked. we had zero idea if it worked or not. We had zero idea what happens before we went and did the experiment. And it was like, oh.
It worked. We are good. We did something great. Okay, I understand why you picked this as the experiment or research project that you're most proud of. Let's say one of the most proud of. I understand that now. The gravity of happiness it must have brought you all, your group and you and your colleagues. That is really cool. Like something that was predicted 30 years ago, and then in the present you just prove it experimentally. Like, yeah, the person who predicted it 30 years ago was right. They knew what they were talking about. That is really cool. That is awesome. So other than doing the research itself, which is so cool and so much fun, what other aspect of being a scientist do you enjoy?
I do enjoy teaching a lot. Okay. So that's something that I did as a PhD student. Mm-hmm. I actually got a teaching degree, like a 60 ECTS credit teaching degree while I was a PhD student. Okay. So my supervisor was very nice for letting me do that during my PhD. Okay. So I did a bunch of teaching on like undergraduate level chemistry courses and then master's level chemistry courses. My favorite was Introduction to Solid State Chemistry because, well, that's where I definitely know what I'm talking about.